Here we are on Geometer Sketchpad. We're about to come up with the law of cosines. Before we do, we're backtracking a little bit. We're going to take a look at a right triangle. This right triangle has sides A, B, and C, where C is the hypotenuse. Now, I'm going to draw some squares on each of these sides. So, the Pythagorean theorem is A squared, which is the area of this square, plus B squared, that's the area of the medium one, should be equal to C squared, area of the big one. Show these area measurements. If I add up the small one plus the medium one, I get the same thing as the large one. Even if I move this someplace else, I still get the area of the large one. Okay, now let's take a look at the converse. Converse of the Pythagorean theorem is if a squared plus b squared equals c squared, then it's a right triangle. But what if it's not equal to? What if a squared plus b squared is not equal to c squared? In that case, we should have either an acute or an obtuse triangle. Right now, I can move this D back and forth. Right now it's an acute triangle with sides A, B, and X. If I square X, I get 64 right now. That's less than A squared plus B squared. When it's less than A squared plus B squared, I get myself an acute triangle. Let's move it to be obtuse. Now look at X. When X is squared, we can see that x squared is greater than a squared plus b squared. Let me summarize this here. If c squared is exactly equal to a squared plus b squared, I know it's a right triangle. Okay, but what if c squared is bigger than a squared plus b squared? I know it's an obtuse triangle. So to make this equation still work, I would have to add in something. If c squared is less than a squared plus b squared, then it is an acute triangle, and I would have to subtract out something in order to make the equation true, in order to make it balance. Okay, so now let's go back to the actual demo for the law of cosines. So I start with myself a triangle, not a right triangle. And I'm going to draw myself a square off of side C. So this side C is going to form a square where our triangle is on the inside. Off of side B, I'm going to make a square just like the Pythagorean theorem one. Color it in, a shade of blue, teal. Now instead of a square off of side A, I'm going to make a parallelogram. Let's color this one yellow. And then on the top of this one, that's where I'll draw my square. Its side length will be A because it's a parallelogram, the opposite sides are the same. Now we're going to finish this off with one more parallelogram up there in the top corner. These two parallelograms will be the same because here's A, and that's A. This is B, and that's B. And they also have the same height. Okay, so here's the question. We're going to let this whole large square, its area, we're going to call that region 1. All the colored bits, the two squares and the two parallelograms, add up that area, that's going to be region 2. The question is, what's the relationship between those two? The area of the big square, area of the colored bits. Answer, they're both the same. I can take these two triangles, I can scooch them right over to this gap. Take the top two triangles and I can scooch them down to that gap. Just watch and see. Just like magic. So this means that the area of the big square should be equal to the area of the colored parts. We'll see more of this in the next part of the video.